So like I said, Gaussian elimination is this algorithm, and what you do is you operate in this algorithm on the matrix. You don't do it by writing out the entire set of equations. It's just shorthand to write it as a matrix. That way I don't have to write x1, x2, x3, blah, blah, blah for every single equation. And all the pluses and all the equal signs. I can just write it as a matrix and perform the algorithm on that. Okay, so let's take a look at the algorithm, though, first, just in the context of writing out the full equations. Okay, so back to our example that we were just working on, where we had 3x1 plus 2x2 equals to 18. And the second equation was minus x1 plus 2x2 equals to 2. And we've already seen the answer to this graphically. But what I can do is I can take that, I can do row operations on here, or these linear operations. And so what I want to do here is I'm going to say, all right, I'm going to take the bottom row, the bottom equation. So I'm going to multiply bottom by 3. And when I multiply the bottom by 3, and then replace the bottom equation with that new equation, I get 3x1 plus 2x2 equals to 18, because I haven't changed the top equation at all. The bottom equation becomes negative 3x1 plus 6x2 equals 6. And so now I have two equations, same two equations, just the bottom one has been multiplied by 3. And now I can also do another linear operation, also known as a row operation, and I'm going to add them together. Add together. And replace equation 2. So I'm going to add these two equations together to give me a third equation, but I can't really have three equations. So I'm going to take that third equation and replace equation 2 with it. So equation 1 stays unaffected, 3x1 plus 2x2 equals to 18. And now I'm going to add these two equations together and write the result here, 0x1 plus 8x2 equals to 24. And now by doing this operation where I multiplied the bottom equation by a constant and then adding them together, it gives me a 0 for one of my variables, a 0 coefficient, which means, since it's a 2 by 2 system, I can just read right off of there almost, what is my x2? x2 equals to 3. Now this process where I sort of intelligently eliminated one of the variables by these row operations, this process is what's known as forward elimination. Forward elimination, and that is the eliminating x1 from my equation. Now once I have my value of x2, I can go back and substitute that into equation 1, right? So I will substitute x2 back into equation 1. So equation 1 says 3x1 plus 2x2, but I know x2 is 3 now, so just put that in, equals to 18. Therefore, x1 equals to 4, right? And so this is what's known as back substitution. So I have two steps to my Gaussian elimination process. I have forward elimination and back substitution. And believe it or not, in both cases, I'm just using these row operations, these linear operations. Multiply by a constant, add two rows together. Okay. So let's do the same thing but in matrix format. Right? So that was just sort of by hand with the equations, but we can do this in matrix format because that's what everyone does, right? Who needs to write out all these pluses and x's and stuff like that? So the first step here is to take my 2 by 2 equation and put it into matrix format. So my matrix format, remember I have x1 and x2 coefficients on the columns, and the first equation and then second equation on the rows. So my coefficient of x1 in the first equation is 3. My coefficient of x2 in the first equation is 2. So that's the first row. Then second row is minus 1, 2. Now that matrix times my unknowns, x1, x2, gives me my knowns, 18, 2. So I have my matrix A times my vector x equals to my vector b. All right, so let's do that forward elimination process that I showed you just a couple paragraphs ago. All right, so the first forward elimination process was I took my bottom row and I multiplied it by 3. So I have 3, 2. Top row stays unaffected. Bottom row becomes negative 3, 6. I still have my x1, x2, which are unaffected. But now my b gets affected. The top one is not affected, but the bottom one gets multiplied by 3. So I have 18 on top of 6 for my b. Right? Then my next operation is I replaced the bottom row by the sum of the two. So the top row stays unaffected. The bottom row becomes 0, 8. X stays unaffected, and B becomes 18, 24. So these two operations, note, affect A and B, but not X. X has one underline. They affect A and B, but not X. And the other thing to note is I did what I wanted here. I got a 0 below the main diagonal. Right, so my main diagonal here, I'm going to highlight that in purple. So I have zeros in every element below the main diagonal. That's what I want. This is what's known as the forward elimination step. Okay. Now, if I want to, I'm not sure whether to call this a step of forward elimination or not, but to finally solve for x2, you divide the final row, the last row, by its remaining element. So if I do that, then my first row, of course, is still 3, 2. My bottom row is now divided by 8 to give me a 1. And since I divided by 8 in the bottom row, I now have a 3 here, 24 divided by 8. Right? So I can read right off of my matrix now, what is my value of x2? Because its coefficient in the last equation is 1. There are no other coefficients in the last equation, and that's equal to 3. Okay, so now that we have that, we have to do back substitution. Now we have to go back and try to eliminate all of the other coefficients that are not on the main diagonal. So to do back substitution, what I'm going to do is I'm going to take my bottom row, I'm going to multiply that by negative 2. Now you wouldn't normally write that down, but I'm going to do it anyway just so you can see the steps. So if I take my bottom row and multiply it by negative 2, I have 0, negative 2 in the bottom row, and then 18, negative 6, right? So you wouldn't normally do this, so I'm just writing this for illustration. Okay, so now that I have my bottom row like that, I'm going to add the two rows together and replace the top row with the sum, right? So that gives me 3, 0, 0, 1, x1, x2 equals to 12, 3, right? Where I went back I rewrote the bottom row back to where it was before because I didn't want the -2 there anyway, really. I was just doing that for illustration. Okay. Almost done, right? We can basically read right off of here what is the value of x1, but to really, finish it off, we divide the first row by its remaining element on the main diagonal and get the final answer, which is actually the identity matrix for my A times x equals to 4, 3, right? And so now reading right off of here, x1 equals to 4 and x2 equals to 3. This, by the way, is what's known as reduced row echelon form. How do you spell echelon? Does it have an S? Does echelon have an S? Maybe. Okay, reduced row echelon form. And what that means is you've taken your matrix with the vector of knowns, B, and you've manipulated everything until you get the identity matrix for A.